Welcome to problem solving session for the course Linear Algebra. I'm Siddhi Balu Ambure from IIT Gandhinagar, and today we will discuss problems related to linear maps, endomorphism, automorphism, image and kernel of linear maps. So let us start with our first problem. Question 1, that determine whether there is a linear map F with the following given properties. Okay, and the first one is F from R cube to R2 with F of 101 is 1, 0 and F of 010 is 0, 1. So
Siddhi, your screen is not fully visible, no, by the way.
what is
Now it is. Now it is. It was my problem. Sorry. Please go ahead. Please go ahead.
Yeah. F from R2 to R cube with F of 1, 2 is 100 and F of, okay, there are three. F of 2, 1 is 010 and F of minus 1, 4 is 001. Yeah, so this is what we have to check. So we have to check whether such F exists or not. Okay, for example, what are the properties of F being linear map? So we say that F from, so let V and W be K vector spaces. Let K be a fill. Be K vector spaces. Then we say that F from V to W is a linear map if first property is that F of so for first is for V1 comma V2 in V, F of V1 plus V2 is F of V1 plus F of V2, and second for some A in K and V in V, I mean for all A in K and for all V in V, we have F of AV as A into F of V. So these two properties must satisfy for F to be a linear map. So for example, when I say that F is a linear map, then addition of two vectors, F operated on addition of two vectors must be addition of F operated on those two vectors. Okay, so for example, if yeah, so we will see whether such F exists or not, such that first one, I want F of F is from R3 to R2, and I want F of 101 to be 1, 0 and F of 010 as 0, 1. Okay, so I just need to check whether if at all such F exists, then whether these properties are satisfied or not. So if you check this F here, I mean, we just want to check whether such F exists. So even if we show that there exists at least one such F which satisfies these two properties, then we are done. We don't have to give information about all the F which satisfy this property. So if you see these two here are same. For example, if I call them x, y, z, then this is x, y. And if I call them x, y, z, then again this is x, y. So if I define my map F to be, just this is our guess, that if I define map F from R cube to R2 such that F of x, y, z is x, y, just x, y, then we can check that F of 1, 0, 1 will be 1, 0 and F of 0, 1, 0 will be 0, 1. And in this case, this f is linear, right? Because f of, if I take x, y, z and let us say u, v, w in R3, and if I take f of addition of these two vectors, so it is x plus u, y plus v, and z plus w. This will be equal to x plus u, comma, y plus v. And if I separate them, this will be x, comma, y plus u, comma, v. And this is nothing but my f of x, y, z and plus f of u, v, w. So this function f defined like this satisfies this first property, and second property, or let me call this a and b. If I take some a in k, or here we are talking about r, so if I take f of ax, ay, az, then this is ax, comma, ay, and this is just a dot x, comma, y. So this f map satisfy both the properties, and it is giving us what we need here, that f of 101 is 10 and f of 01 0 is 01. So but this is not the only map which will give us this property. For example, you can also define it to be f of x, y, z, because if I call this x, y, z, then this is also let me keep this as it is, and let me use another color. This, if I call x, y, z, then this is also z, comma, y, right? And if I call this x, y, z, then this is z, comma, y. So I can also define this map, and you can check that this again. So in this case, this f will be defined as f from R3 to R2 will be, in this case, x, y, z going to z, comma, y. And not only this, we can define it in very different way. For example, I can also define it like, let me choose another color. If I take this x, y, z, then I can also take it. I want here 1, comma, 0, right? So I will do this x plus z by 2, comma, 0. Sorry, comma, y. And here also it satisfies this, right? Because 0 plus 0 by 2, the first coordinate will still be 0 and second coordinate will be 1. So there are different f which satisfy this property. For example, we can define f of x, y, z to be as we saw earlier, z, comma, y, and f of x, y, z to be x plus z by 2, comma, y, and so on. We can define this f in many different way, but to check whether such linear map exists or not, we just wanted to show one, and we could see there are many such. So yes, so this is done for the first one. So yes, this is true. So f exists in this case. Yes, sir.
That was my doubt actually. So you explained it now here that the f x comma y comma z can be defined as x y or y z or x z anything. There can be n number of linear functions, but just to show they are linear, we have to just show in one way.
No, we are not. Here the question is determine whether there is a linear map. So we just have to show whether there exists linear map which satisfy this or not.
Yes.
Okay. Yes. So as long as this 101 and 010 take these two property, my f could be anything. As long as it is linear, that's what. So these maps, so for example, here, the way we define this f here, we actually proved that yes, this f satisfies the linear property. This f xyz is equal to f of xz, f of xyz plus uvw, and this one. So you can check that these two, if I call them this, if I take this one, if I call them 1 and 2, you can check that these two maps are also what we can say are linear maps. So as long as I have linear map which satisfy these two conditions is what we need to check. That's it. The existence is what we have to prove here. Show. Sorry.
Okay.
Yes.
So need not be this fxy like here.
Yes.
If you go little up, yeah, f of 101 is like f of 101 is equal to 10 in the first one. This 10 can be xy also, can be xz also, can be yz also.
Not all. I mean, see, I mean, if I take xz, then in that case, this will be 1 comma 1, right? If I define my f from,
okay,
yes,
okay.
exactly. It should be. That's why here also, when I added x plus z, I divided it by 2 because addition of xz will give me 2. But I want first coordinate to be 1 here.
Okay.
Here,
So you
this
mean to
blue
say
one.
it should come, the output should come as 1 comma 0.
Yes, exactly. We want f which satisfy these two properties. So yes, exactly. That's what we need to. And if, yeah, I mean, this is our aim that f of 101 should be 1 comma 0 and f of 010 must be 0 comma 1. As long as these two conditions are satisfied and I'm defining a proper linear map, by proper I mean the well-defined linear map, that's okay. And there are many ways. I mean, we just showed that this is one way.
That's why
Yes.
you mentioned is zy, not yz. Okay.
Exactly, because yz will give me, for here,
Yz
it will give
is
me
0
0
1,
comma 1.
which
This
is
is
not
not
the
what we want. And
right.
here
Okay.
also it will be problem. It will be still a 1 comma 0. This is not what I want here. So
okay.
yes, so that's why when I took xyz, it is yz, zy, and then here to make the first coordinate 1 comma 0, here I divided it by 2 in first case because 1 plus 1 divided by 2 will give me 1 in first coordinate and 0 is added as it is here.
The same thing should also applicable for the second equation, na? F010.
Second, exactly. The 0 plus 0 by 2 will be still 0 and y is as it is. 1 here.
Okay. So there can
Yeah.
be n number of, okay, but we have to find
Yes.
out, okay.
Yes. We just wanted to show whether such map exists or not. That determine whether there is a linear map which satisfy this property or not. So we just wanted to give at least one linear map which satisfy this property.
Which we did, which one we satisfied here? I mean, which one we mentioned here? It is a linear map. We just show the property here, na?
Sorry, sir?
In the down where you have marked the yellow color, we have shown the property that if it is a linear map, then as you mentioned, f of
This is satisfied here. And this is linear map. This is we are proving that f the way we have defined is a linear map by proving these two properties.
हमने प्रूव कहाँ किया इसमें तो हमने as it is we have just mentioned it here f of x plus 5y plus
This is proof, right? For any x, y, z and u, v, w in R3, I proved that f of their addition is addition of them, and f of a into that term is f of a. This is what we are proving, right? This is property of linear map. See here.
so that is the
This is,
property of linear map. That is yeah, these
and
are the
that's
two
what
of the
we prove here.
properties.
This is proof of linearity of f. Proof of This is proof of f being linear. Proof of f is linear.
But have we used the values of the 101 and all that here in the
Because
proof?
in the proof we do not need to use, right? I need to prove the map is linear.
The map is
F
linear.
satisfying these two property is there already. We checked, right? Yes. For example, if I ask you to if I want you to define map from R to R, such that f of 2 must be 4, then how will you define it? And I want it to be linear map. You can define f from R to R such that so it could be, you can define it like, sorry, R to R, x going to x plus 2. This satisfies, right? This condition. Or I can define x going to x square. My screen is frozen or what? Hello.
Hello. It is audible.
There was some internet problem. Yes. Sorry, we were here. Really sorry. Yeah, so what I was saying is, so we were here. Sorry, yeah, so your question was, am I here? Oh, okay, okay, I am here. I hope I am still audible. So the question was, yes, so the question asked was that whether we use this here or not. So see, the way we have defined f here, xyz going to xy, already satisfy these two properties. Now I have to check. So see, this question asks these two properties, whether f is linear, and the second property we need to check is these two, whether it satisfies these or not. So the way we have defined f here, this one, is satisfy these two property by default, right? The way we have defined. Now I only need to check whether this f is linear or not. And we have actually checked it by using this. I mean, I took if I call them v1 and v2. If I take this v1 here and this is my v2, then this is f of v1 comma v2, and this is f of v1. This is f of v1 plus v2, right? And here this is f of a v1, and this I proved is equal to, this is what? This is a into f of v1, because f of v1 is x comma y. So what I was saying is that when I'm asked whether can I define a linear map from R to R such that f of 2 is 4, there are various ways we can define a map f from R to R such that f of 2 will be 4. For example, I can prove, do it like x going to x plus 2, x going to x square, and x going to 2x. But out of which one is linear? So this is, for example, if I call this f1, f2, and f3. All these three maps satisfy, I'm audible, I hope.
Yes, yes.
Yeah, thanks. So all these three maps satisfy this property. F of
Yes.
2 going to 4.
Yes.
But are all these linear maps? No, right? Because here, see, this is not, because f of 0 is what? 2.
2.
So this is gone. I told you last time, sometimes we can use 0 to exclude whether f is, yeah. This one here, if I take f of x1 plus x2, this will be x1 plus x2 square. And this is x1 square plus x2 square. This is my f1, f of x1 plus f of x2. Plus, but this also has this extra term, 2x1, x2. So this does not hold, right? So this is again not a linear map. But this one, when I take, then for all, this is f of x plus y whenever I take. This is 2 into x plus y, right? So this is 2x plus 2y. And what is this? This is f of x and this is f of y, right? So this map is linear. And second property, f of ax will be 2 into ax. This is a into 2x, and this is my a into f of x. So this map only satisfies the linear property. Okay, so that's what is asked, whether we can have at least one map such that this is satisfied.
Acha, okay. Whether do we have one map? Okay, okay.
Yes, so one map here is this, we satisfy that property, but we saw that there are many ways we can define a linear map. A linear map which satisfies this property, yes.
Okay.
Okay.
Thank you.
Yeah, sure. So similarly, now we have to check the second one. So this one, f exists. So now we have to check whether for this second map, whether such f exists or not. Okay, so second one is f from R2 to R3 such that second one is f is from R2 to R3 such that, yeah.
So, just a question, Siddhiji. When you are saying it goes from R2 to R3, okay, it is in strict sense is going from 2-dimensional vector space to 3-dimensional, right?
Yes, sir.
Plane to volume, for example, right?
Yes, yes.
So these linear maps, can they go from say R2 to directly R4 or R5?
Yes, whatever we can define it the way we want. For example, I can very well choose, for example, if you want to define it from R5, any, give me whatever. We can also
So my
define it
question
from,
is,
yes,
let's
sir.
assume that you are going from R2 to, let's say, R10, for example.
Okay, R2 to R10. Okay.
So what will be the difference between these two maps? How different they will look from each other in the sense?
I mean, see, R10 means there are 10 coordinates, right?
Yes,
Yes, and R3 is there are only 2 coordinates.
three
So
coordinates.
yes, sorry, yeah, 3 coordinates.
Huh.
Yes, I mean, so the way we are defining map, I mean, here when I say F is like this, R2 to R3, it will be
So
some F
R2
of
to
x,
R3,
comma,
you took F as 2x, right? In our earlier example.
in earlier example, yes, where?
That what was that F function?
This,
2x,
this
right?
one, yes, 2x, yes. Because this is
So
R to R. This is R1 to R1. So there is only one number here.
okay.
Coordinate is only one. Okay.
So what was
Yes.
the map for R2 to R3 that I have not still understood earlier?
Earlier, what, sir?
No, you gave that example now from R2 to R3, f of x y z map to zy, right? So
Here it
what?
is from R3 to R2.
Yes, f of x y z to xy.
Yes. So this is,
So
see, this was,
what was the function? Like here you took from 1 to 1 fx as 2x. So here what
yes.
was the function in that?
Here F is defined like this. F of x, y, z is, so yeah. So let me just write this explicitly. In the earlier example, F is from R3 to R. Oh, let me write it here only. This is
I
my
Maybe I
want to
think
function.
see, I want to see
maybe I,
how different they will be, right?
F
Vinayak,
by
Yeah.
R3.
I think if it is only one coordinate, it will be a point. But if we are going from R to R2, it will become a line. And if you
Correct.
go from R2 to R3, then it may become a plane. And if you go
Yes.
for R4, R5, it may become some contour, which needs if you say R10, then it needs
Something
10
in 10th
coordinates to draw
dimension.
something like that, 10 points
Correct.
to draw that plane.
Absolutely. So I just want to see how those linear maps will look different. I
So
mean,
for example, linear maps will look different. For example, here F from R2 to this one, R1 to R1 will be what? This is my what I can say. To draw a graph, I need
let's take the
this.
same example, na Siddhiji. See,
Yes,
you
sir.
here for R1 to R1, you took F3 as x,
Going to
x as
2x.
2x, for example.
Yes.
Correct?
So if this is my V, that is R, and this is my W, that is R. So if it is going from V to W, both are R, then it is this line, right? This is my 1 and this is my 2. That's it.
Correct.
This is a line here.
Correct.
And here, if I want to draw a graph of this function, it will be in 5 dimension, right? What I can say, domain will be of 3 dimension, codomain will be of 2 dimension. So it's difficult to, I mean, but the
No,
image for
not
given,
drawing,
yes, sir.
but here I could see the function fx as 2x. So here, what was
Yes.
the function from R3 to R2?
Here the function was xyz. This is projection on xy axis here. This is projection on R2. Projection of R3 to R2 here.
Okay.
XYZ going to XY. And if I just want to look at it in XY, R3 to R3, so this is XY comma 0, I would say. There is nothing as such in the third coordinate. So this was projection on what I can say, XYZ going to XY. So this is just, I'm ignoring whatever there in the third coordinate and only considering these two. The
Then
way
that
I
could
have
be
defined
if xyz as xy, or it could be just yz or xz, right? There could be three
Yes,
different
yes,
possibilities here. Correct?
exactly. Yeah, that's what I told you. I mean, we can also define it as XYZ going to Z comma Y. Then this is some kind of
Okay,
rotation
but
and then taking
if it is say
projection.
reverse, you were to go from R2 to R3, then
Yes.
f of xy would be what? Here there
Here,
was projection, right? You just reduced one coordinate to 0, you annihilated one dimension.
yes.
But here you are adding one dimension from R2 to R3. So
Yes, yes, that's not a problem, right? For example, if I can also define F from R2, okay? right? Such that my x is going to 2x comma 3x. Just this is well-defined map, right?
Okay.
Okay. And what it will be in XYZ plane, if I want to, I don't know how to draw it in 3 dimension. But where, for example, this is my x, this is my y, and this is my z. So x here will go where? 2 comma 3, right? So this point will be, so for example, this is my 1, my y is 2, and z is 3. Then this point will be some 1 comma 2 comma 3. This will be
Yeah,
image. So
somewhere in that. I can visualize that. Okay.
yes, exactly. So because this is R to R2, we can visualize this. Since this is R2 to R3, this will be some 5-dimensional thing which we want, I mean, which we
Yeah,
can't imagine.
so that's what I'm
Yes.
saying. I don't want to visualize it. Like
Yes.
like you mentioned here, from R2 to R3, you gave 2x comma 3x. So in that example, R2 to R10, what probable function you can write for mapping?
Whatever. I mean, see, I mean, if we can see any function, for example, x comma y going to just take xy 10 times or 5 times. It will still be linear map. Or we can take x plus y in each coordinate. Or we can just take x comma y and then rest is x plus y and rest all are 0. Whatever we want. We can define the function whatever
But can
way
it be
we want.
like, different? See, for example, that R10 is a vector space in 10 dimensions. So it will have 10 bases, right?
Yes.
R1, R2, R3, and R10, correct? 10 different uh, bases, which will be spanning that R10 space. So that
Mhm.
fxy map to R1 to R10, will that be a linear map?
Yes, it will be a linear map.
Okay.
But I mean, see, there is also one way. So this is one way. So for example, if I take this Rm to Rn, if I want to define, then each coordinate is some function. So this is, then for each, if I define f1 to fm from Rm to R, okay, Rm to R, these are n functions, if I define, then this f from Rm to Rn will be just x1 to xm going to f1 of this x1 to xm, fn to x1 to xm. So each time what you
Okay,
are
okay,
doing is
okay.
you are defining f from Rm to R, and for example, for this 2x and 3x, what I'm doing is I'm defining f from R to R such that f going x is going to 2x, and second, this is my f1, my f2 is x going to 3x, and then my original function f now becomes f from R to R2 as f of x is going to f1x comma f2x. And is that okay
Yeah,
now?
somewhat I'm getting. Okay.
Yes, yes. So for
It
each
is
and
not
each
possible to
coordinate,
visualize 5 coordinates or 10 coordinates.
yes, does
After
not matter.
three,
So here you
yeah,
can
after three,
always
it's very
define something
difficult
like
to.
this, right?
Ha, ha, ha.
Now this is, I
Yeah.
think, it's easy to understand what is happening. At least, I mean, not the
Right,
visualization,
right,
but the
right.
idea of how the
So
function
each
is defined.
function of all the coordinates repeated n times when you map over there.
Not
I
repeated. There could be completely different
different, yeah,
functions.
not repeated. I agree. Different
Yes, yes,
functions,
yes.
but the functions will have all the coordinates from the original vector space M,
Yes, yes.
right?
If this is my V and this is W, then yeah.
So if I'm
V to,
transforming R2 to Rn, for example, then I will have F1 x1 x2, F2 x1 x2, F3 x1 x2, like that, Fn x2 x1 x2,
yes,
n
yes.
functions of that particular space.
Yes, exactly. And then
And
you
and
place
what
them
will be
in
that
each,
function? That function will be linear always, right? It won't have any.
because each f is linear, this will be linear. Because see, each f1 is linear. So at each coordinate, this will split, right? And then it will be addition of all those.
So that F1 also of x1 and x2 can be, for example,
These are all linear. These are all linear.
Because earlier you showed a function of just x, f of x as 2x. So, but
Yes.
x1 and x2 will be like, for example, 2x1,
So see, in
comma
this case,
2,
how we will define?
3x2,
Okay.
something like that, correct?
So see,
So,
let me just define. Let me just show how this map is linear. Okay, this you are saying that how we are showing the linearity in this case. That's your question.
so right,
So
right.
this
Here
I
you mentioned.
already
So,
proved, right?
just,
This
just scroll
here.
down, scroll down. I get your point. Just scroll down a little bit.
Yes, sir. Yes.
You just answered the thing. See, here you already mentioned that function is 2x comma 3x because it is in R2. So I was saying x1 comma x2. So that f2, so this is f1, for example, that you are showing.
F1
Let's take
is
same
my
example.
here. Yes, F1 is from R to R now because my domain is R here. So this is x going to 2x. And F2 will be my R to R, x going to 3x.
So
Right?
likewise, going
Yes.
to R2 going to R10 will be f1, for example,
Yes,
2x comma
F1 from R
3x.
to R, F2 from R to R, and such, and like that F10 from R to R.
R2
And
Rn, not
no,
R10,
R
right?
to R. And then see, I mean, and then F will be from R2 to R10. This is just a way of understanding. It's not exactly how the functions are defined, but just now this will be this R2. So here this will be some x comma y, right? X comma y going to. Here everything is x comma y going to this f1 of x comma y, right? This here x comma y is going to f2 of x comma y. And here my x comma y is going to f10 of x comma y. This is just image. And now I want it to be in R10, right? So in first coordinate, I will place f1 of x comma y. This is now some number in R. And this is f2 of x comma y. This is f10 of x comma y. And everything is linear. This is R, and this is 10 times.
Got
So
it.
this is in
So
R10.
F1, so for example, I can define F1 x comma y as say,
Whatever
say,
you want. Whatever
yeah,
you want.
2xy,
Doesn't matter.
for example, right?
3x, 100x, whatever you want. Does not matter. As long as F1 is linear map, all these Fi's here are linear map.
But
This is
are these
verified.
functions from R2 to R10, are these unique or
No, not at all. Why it would be unique? I mean, x comma y going to, I can take 0, 0, 0 everywhere. This is one
okay?
function.
But
Then x comma
let's
y
assume for
going
a
to,
second. Let's assume for a second that my R2 is xy is a plane, for example, xy plane. There is some curve on that plane, okay, and now I want to project this curve into R10. So, and if I know in R10, let's assume for a second I'm a being in R11 and I can see R10, visualize R10, and there is a particular shape of that curve, same points how they are projected. In that case I can use particular functions, but when I'm not in position to map them, it will be some functions which hello.
I'm audible, right? Okay.
Yeah,
Could you
you're
please
audible.
again? Yeah,
You're
yeah.
audible.
Yeah. Could you please again repeat, sir? What were you saying just
No,
now? Because I couldn't hear.
just one thought process that I had.
Yes, sir.
Let's say, for
Yes, sir.
example,
Yes.
I have a planar, curve, say semicircle, okay, or a line, let's say, in
Okay.
XY plane, and in 3D, I'm mapping that line. Say in XY, that line is from 0 to x0 y0 and x1 y1. It's a
Okay.
45-degree line in XY plane, and I am mapping that line in a 3D now, where it is going from x1 y1 z1 as 1 and x2 y2 z2 as 2, from 1 to 2. Planar line going into a 3D line. Now we
Okay.
know that 0 0 has to get mapped to 1 1 1, and 1
No,
1
no.
has to
0,
get
0
mapped
needs
to.
to map to 0, 0, 0. 0 needs to map, 0 will always map to 0. That's the definition of, that's what linear map means. Because see,
Okay,
f of
fine.
AV will be A into V, right? So f of 0 must be equal to 0V. So yeah,
Okay,
0
fine,
must
fine.
go to 0.
So say 0 1 line now getting transformed into 0 0 0 to 1 1 1. So that 1 1 will get mapped to 1 comma 1 comma 1. Correct?
What you are saying that, could you please again define the way, what you want to, whereby f is going from what? R to what?
R2 to
F is
R3.
going, okay, and such that
Such
f
that
of,
let's say on a plane XY there is a line now.
okay,
The start point is 0 0 and end point of that line is 1 1.
0 0 1 1.
Ah,
Okay, 0. Okay, so you are taking this in R2.
ah,
This is your line.
correct.
Yeah,
And now
okay,
this mapping it, I want to map that line in R3 now.
okay,
Where
okay.
end point is start point will still remain 0 0,
0
right?
0 0.
And end point will become 1 1 1 now.
Yeah, we can have that map. So in that case, you are saying XYZ is going to XY, sorry,
Um,
XY is going to
XY
XY,
is going to XYZ.
and XY, yes, here either you need to put X or Y, or what I'm saying is here something needs to be in R3. So if I want this to be some alpha, then
Ah,
it should be such that you want this 1 comma 1 map to 1 comma 1 comma 1. That's your idea, right? This is
yes,
how you want your map to be. This f
yes,
is such that it is taking this 1 1 to 1 1 1 comma 1 comma 1, right?
yes.
So there are many ways to define it. You can either define it x comma y going to x comma y comma x. Now this 1 1 1 is going to 1 1 1 without any problem, right?
Okay,
Because x was 1 and this is going to here 1. This one is going to 1 here. Okay,
okay,
or I can define x comma y going to x comma y comma y. Now this one here, this y coordinate one is going to again this third one here, because 1 1 is as it is, xy are going to xy, that's not a problem. Or
okay. But
you can also define, this is what I was trying to explain, that there are many functions which can take you to that map. For example, x comma y. Now again I want my third coordinate to be 1, so I can do it like x plus y by 2, right?
yes,
Yeah, yeah. Because in this case, this one will going to, this will be 1 plus 1
got
by
it.
2. Yeah. So now this is 1. The last coordinate is again 1. So here
Okay.
this is was my 1 1, and that is going to 1 comma 1 comma this one. So there
So
are
in
many
terms of
ways.
functions, I can write first on the right side those xy and xy x plus y upon 2, these three. In terms of function, I will write f1 x comma.
So yes, so if you want to write this as function, see, and you do not need to have this first coordinate as xy. Even here you can define it to be x comma x plus y by 2 and x comma x plus y by 2. Does not matter, because as long as this point is mapped to this point, any f would work. Linear.
Okay.
Yes, this is also a well-defined function which is giving me this condition. Can you see this? Because in this case also, the second coordinate is giving me what I can say, 1 still. Let me choose this color. For example, here 1 comma 1 is going to what? 1 comma 1 is going to 1 comma 1 plus 1 by 2. Still 1, 1 plus 1 by 2, still 1.
Yeah. And
Yes.
if
So
the
there are,
coordinates change, then I have to change the combination. Like it can be 2x plus y upon 2. So that will be 1, 1.5, and 1.5, something like
yes,
that.
yes, yes,
So
yes, yes, yes,
can change
definitely,
them.
definitely.
Okay,
Sure.
I agree. I understand.
Yes,
So,
yes.
but in terms of the functions now, okay, on the right side, how I can write that x as f of f1 of xy, which is
Yes.
nothing but x.
It's just x.
Ah,
For example,
then
if I'm
f2 of
talking for
xy, which
this
is x
f,
plus y by 2, second
yes,
function.
x comma y. If I'm which function you want to talk about? 1, 2,
Second,
3,
no,
4.
that will be f2 will be x plus y by 2, and f3 also
Yes,
will be x
exactly.
plus y
X
by
plus y by 2 and f3 will be again x plus y by 2. Yes, exactly. This is how my functions are defined. Now this will be equal, not
Then I can generalize by saying f of xy. Now, instead of saying f of xy, I can say f of a b c d up to n whatever, and then a linear. I mean combination of those coordinates for that function, and
yes,
second function and third function. And those combination is something that I can decide. Those combinations have to be linear only.
yes, exactly. As long as that's happening, we are okay. Is that okay now?
Yeah, somewhat. I still a lot
Yes.
of doubts, but let's go ahead. I don't want to stop you, please.
Yeah, sure. Yeah. Yeah, so second one was this. So now the second one would maybe help you to understand. I'm still audible, I hope. Yeah. R3 to R2 to R3 is my function now. R3, and such that f of 1 comma 2, I think it's gone. I was, let it be. Does not matter. F of 1 comma 2 is 1 0 0. F of 2 comma 1 is 0 1 0. And f of minus 1 comma 4, I want it to be 0 0 1. So see, now I have three equations. F of 1 comma 2 is 1 0 0. F of 2 comma 1 is 0 1 0. And f of minus 1 comma 4 is 0 0 1. So so what I want is that f is from 1 comma 2 to yeah, so what I want is that this three should satisfy, right? I mean, if so, for example, if this is the one information given to you, and if you are also given extra information in this example, for example, you are also given that f of 2 comma 2 is f of 2 comma 2 comma yeah, for example, f of 2 comma 2 comma 2. Is this will this will always be following that path, right? Oh, or I can say f of 2 comma 2 comma I want it to be linear. So yes, I can do this. F of 2 comma, how to do it? Or maybe 2 comma 3 goes to 3 comma 2 comma 2. If this is my function, for example, okay. Now I want function f to be such that this is happening. So 1 comma 1 comma 1 is going to 1 comma 1 comma 1, and my 2 comma 3 is going to 3 comma 2 comma 2. So what will be your function? How will you define it? So if I take my f to be this, x comma y going to f from R2 to R3, x comma y going to x comma y comma x, or yeah, then this is satisfying this first point, right? The green one is satisfied here, but this purple or whatever color it is, this point is not satisfying this, right? 2 comma 3 in this case will go to 2 comma 3 comma 2. This is not what I want. I want 3 comma 2 comma 2. So how will I define my function? X comma y going to, I want 3. So 3 in the first, so this is y here. And then 2 comma 2, right? I mean then x comma x. So the earlier one, when I was dealing with only 1 point, 1 comma 1 going to 1 comma 1 comma 1, all these functions could satisfy this property. But as long as I also give you extra information that this 2, 3 must also satisfy certain property, in that case, none of this is helping. All these functions which we defined here. I had to now look at completely different function, and it was this. F of now x comma y, I'm taking it to be y comma x comma x. Or yeah, y comma x comma x. This is one of the way to define that function. Okay. So do you understand what I'm trying to say here? That whatever information is given to us, we have to check whether all of them are satisfied by the linear function or not. So if I give you, for example, one more point here, say whatever, suppose here, if I take -1 comma, suppose 1, and if I ask you to have something like this, -1 comma, sorry, I want this to be -1 comma 1 comma 1. Then can we define such function? And so on. So that's what our problem is, that as long as certain images are given, can we find a linear function satisfying those properties or not? So that's what we will do. So two functions. Yes.
I think anything in the negative will not be satisfied. No? Otherwise, how will get a negative sign? This does not look, because f of -1, 4, is how will we get this minus? Okay.
Yeah, it will be right. F of -1 comma -1 will be, if I take this.
There can be, right. There can, maybe some addition.
You are muted, sir. Hello.
Yeah, please go ahead.
I could not hear you. Yeah. Yeah. Here the -1, see the way we have defined here function, -1 comma -1 would go to -1 -1 -1. So yeah, -1 is satisfied. That's not a problem. And in fact, -1 comma 1 will go to 1 comma -1 -1. Minus is not a problem here. This xy, when I define here, it is anything from R. It has nothing to do with x being positive or negative.
Okay.
Yes. Okay, so now what I want, if f is linear, if it should satisfy this. So see, we are in R2. So R2 dimension 2 is there. So as long as I have two linearly independent elements, it will generate my R2. And it is also, I mean, this remark or theorem or whatever you want to consider, if f is from V to W, V and W are K vector spaces, suppose, and K is filled, then f and let V is equal to, let this V1 to Vk be a basis of V. Suppose V is that, and by this I have dimension of V as, let me not take K, N. Then this f of V1, f of V2, f of, then this f of V1, f of V2, and f of Vn will gives, oh, yeah, this Vn will give us entire information about, or yeah, will give us, I mean, this is enough for us to, this will, what I can say, yeah, let me write this. This is not really correct way, but entirely. What I mean by this is because for any V in V, this V will be some A1 V1 plus AN VN, right? So this F of V will be what? This A1 F of V1 because F is linear. As F is linear, I have this plus AN F of Vn. So just having information about map on, sorry, information about F on its, on the basis of domain, we can get the entire information about the F. That's what we're gonna use here. So I can use that. So for R2, we can have this basis 1, 2, right? Basis of R2. Let me write this. Basis of R2, I can take. It's not compulsory we have to take these two, but since these two are easier to deal with, I will take, this is basis of R2. And if at all such F exists, so if I call this star, if F from R2 to R3, a linear map satisfying linear map satisfying star exists, then f of a 1 comma 2 comma b 2 comma 1 will be equal to a f of 1 comma 2 plus b into f of 2 comma 1. This will satisfy, will satisfy, okay? And so what I will do is I will try to rewrite this minus 1 comma 4, right? That's what is, yeah, as linear combination of f1 comma 2 plus b2 comma 1. Okay, and if f is linear, if f is linear and exists, I mean if required f exists, then this f of minus 1 comma 4 will be what? This a, whatever we will find, will be f of 1 comma 2 plus b into f of 2 comma 1. This will happen. And if this is equal to, so whatever, this is anyway given, and when I find this a and b here, if whatever I get here, if that is equal to f of minus 1 comma 4, which I want to be 0 comma 0 comma 1, if this happens, if these two are equal, then we are done. I mean, are you able to understand what we are trying to do here? We are trying to obtain a linear combination of these two vectors here. If I call them v1, v2, I will denote this v3 in terms of v1 and v2. And if linear combination, whatever happen here, will give me this third one here, then I will conclude that such f exists. Okay, we will see what is, I mean, when we actually do the calculation, it will be easier to understand. So what is given here? What we are given is f of f of 1 comma, I want this to happen. I want to find this linear combination. So if I compare coordinate wise, this is a plus 2b is equal to minus 1, right? And 2a plus b is equal to 4. And if I satisfy, I mean, if I do the linear combination thing, this will be 3a plus 3b is equal to 3. So this will give me a plus b is equal to 1, and subtracting will give me minus a plus b is equal to minus 5, I guess, if I'm not minus 5. Yeah, minus 5. And then using these two, I will get 2b is equal to 2b is equal to minus 4. So this will give me b is equal to minus 2. And using this, I will get a is equal to, I mean, this one here, I will get a is equal to It is 3, right? Yeah, A is equal to 3. So with this A, so 3, 1, comma 2 plus minus 2, 2, comma 1 is minus 1, comma 4. We can check here, right? This is 3 minus 4, giving me minus 1, and this is 6 minus 2, giving me 4 here. So this is there. This is completely correct. So now if such exists, if f exists, then f of 3, 1, comma 2 plus minus 2, 2, comma 1 will be equal to f of minus 1, comma 4. This will happen, will be true. Okay, but what is f of this 3, 1, comma 2 plus minus 2, 2, comma 1? It is 3 into f of 1, comma 2 plus minus 2 into f of 2, comma 1, right? By the definition of linearity, because we are assuming f to be linear. If such linear map f exists, then this happens. And then this is 3 of f1, comma 2 is 1, 0, 0 plus minus 2 into f of 2, 1 is 0, 1, 0. And this is 3, comma minus 2, comma 0. And is this equal to, and what is f of minus 1, comma 4? This is, where is it? It is 0, 0, 1. And these two are not equal. So therefore, hence no such exists. Because what I wanted, f to be linear and it should satisfy all these three equations here. Sorry. But that is not happening. The moment these two are satisfied, this third one is not possible. And if you, and this is the only possible way to do this. So this actually gives us argument that no such f exists. Is this okay? You can also try it with these two and try to come up with linear combination of 1, 2. So try to do something like this. C of 2, 1 plus D of minus 1, 4 is equal to 1, 2. And check that whether f of this thing is equal to f of, let me use this f of this thing, whether this is equal to f of this or not. And we can see that, you will see that this is not possible. And you can try this with other two, or you can take you understood, right? You can take f of v1 and v3. So f of v1, so you can try this v1 plus v1 plus f, let me write. You understood, right? You can take this minus 1, 4 is equal to 2, 1, and then check that f of this thing, whether is equal to f of this thing or not. And you will see that it is not happening. And no such f exists. So because if such linear function exists, then it must satisfy these properties. Is it okay that no such f exists?
Yeah, that's fine here, it seems.
Yeah. It is correct. No such f will exist, because if it has to exist, it would satisfy this condition. That is not happening. And also this is basis, right? This is basis. Where is it? This is basis here. So if at all there is a way to represent minus 1, 4 using these two vectors, it is unique. So this f, if at all it exists, it will be uniquely defined on the basis. Once the basis is fixed, the way I want to define f, it will be unique. If for example, f is there, I have a basis, and at each element of the basis, f will take some value. And any other, if I want to represent image of any other vector using that basis, then there is only unique way to do that, because that V will be represented uniquely using this basis. Is that okay? I hope it was not confusing the way I said it. I mean, I'm just saying that once I have the basis, this linear combination here, this is unique for 1 and 4, for this -1 and 4. So yes, and since this is not happening, this F is not possible. I hope that is okay. And I will just quickly go through this one more question which is related to this, and we can check whether it is happening. So for example, this question that yes, what they are saying is that this, since we are already calculated this, there exist, let us check, unique R linear map. So this is what I was saying, this uniqueness which I was trying to explain here, R2 to R3, such that h of 1 comma 2 is 1 0 0 and h of 2 comma 1 will be 0 comma 1 comma 0, and the value h of -1 comma 4 is uniquely determined. And they are asking that what is the value. Since the map is uniquely defined, of course, this will be uniquely defined. What is the value of this h of -1 comma 4? That is the question. And secondly is that determine whether yeah or not there exist two R linear maps f from, and this is different, okay? This is f, when I say see here, the unique is for this uniqueness. Okay, let me just try this. This uniqueness is because of this thing. Because this is my basis, and on the basis I have defined the function. I know the image on the basis. That's why I know the uniqueness of that map. Okay, and here it is completely different. They are saying that two maps f and g, such that now they are asking this, whether f of 1 comma 2 is 1 0 0, f of 2 comma 1 is 0 1 0, and f of -1 comma 4 is 0 0 1 or not. And I want g to be g of 1 comma 2 to be 1 0 0, g of 2 comma 1 is 0 1 0, and g of -1 comma 4 is 3 2 0. And we will see that is happening or not. So here what they are saying is that there exists unique R linear map h from R2 to R3 such that h of 1 2 is something and h of 2 1 is something, and the value of h of -1 comma 4 is uniquely determined, and what it will be. So see that for the first one, since uh, h is from R2 to R3 and a basis of R2 is this 1 comma 2 2 comma 3 2 comma 1, sorry, and for any v or any xy in R2, we know that xy will be some a times 1 2 plus b times 2 1, right? And this a and b are unique. I mean, you can do this, okay? I mean, we will again have to solve this equation, a plus 2b is equal to x, and 2a plus b will be y. And then solve this, that 3a plus 3b is equal to x plus y by, x plus y. And then a plus b will be x plus y by 3. And then subtraction will be, here it will be minus a plus b will be x minus y. And when I subtract, I will get 2b is equal to x plus y by 3 plus x minus y. And this will be something, whatever here it is. And then I will have the value of b. Or you don't even have to do that. Just choose that b is x plus y by 3 plus a. Sorry, minus a. And if I substitute this in one of these two equations, or plus a, and if I substitute it here, oh, I can't do that, right? No, it is correct. B is my x plus y by 3 minus a is equal to x minus y. So this is minus 6a plus x plus y is equal to, this is minus 3x minus 3y. So this is minus 6a is equal to x 2x minus 4y. So my a will be something. A will be my,
minus
a
x
will
by
be
3.
minus x by 3 minus 2 something. Here it will be also something. 2 by 3. 2 by 3 y plus minus x by 3 and this. And using this, I will get some value of b. Oh, a is this. Let me just do this. Minus x by 3 plus 2 by 3y. So this is x is, no, this is 2x plus 3y, right? 3y by 3. Something like this. So it is 2x, and this was minus, right? So y minus 2 will be minus. So this is minus y. So this is 2x by 3 minus y by 3. Okay, and so for any xy in R2, this is uniquely written as minus x by 3 plus 2 by 3y into 1 comma 2 plus this is 2x by 3 minus y by 3, 2 comma 1. And the moment I have this, f of this xy will be uniquely determined, right? These are unique. The moment I fix this xy here, this is unique. This a and b become unique. There is no other way for this a, b to exist. So,
Siddhi. So this is what I was asking, that there will be a
yes,
unique function, but when now it is easy to solve this unique
yes,
function in
yes.
2 to 3. Okay, I mean you are coming from 2 dimensions to 1 dimension to 2 dimension, or 2 dimension to 3
I'm still
dimension.
going,
It's solvable.
see, at this point, I don't care where the image set is. Here, this, all the, so far, everything here. So far, everything is
In
happening
R2.
only in R2.
R2.
At this point, I do not even care what my codomain is. It could be R power 100, it could be whatever, it could be R. I don't care. At this point, everything is happening only in R2. As long as I have the information about R2, what is happening in R2, my image is defined. So see here, what I'm saying is, if I have, now I have this f, right? F is this, I mean H. I wanted it to be h. Yes. My h is from R2 to R3 such that what they want is 1 comma 2 going to h of 1 comma 2 is, what is it? It is 1 comma 0 comma 0, and h of 2 comma 1 is what? It is 0 comma 1 comma 0, right? So what it is? So f of xy will be what? This is f of this, right? Sorry, h of xy will be what? H of this thing, h of minus x comma 3 plus 2 by 3y, h of 1 comma 2, right? Plus this constant as it is, 2x by 3 minus y by 3, h of 2 comma 1. And whatever it is, I will just substitute here this as it is. It is 1 comma 0 comma 0 plus whatever here it is, 0 comma 1 comma 0. And this is how my function is defined now. If I here, so what it is in the first coordinate, it is minus x by 3 plus 2 by 3y, comma, in the second coordinate, I mean just adding this, or let me just write this here so that no one gets confused. Here it is 2 by 3x minus y by 3. And yeah, so this is 2 by 3x plus minus y by 3, comma 0, right? And this is my h of x, exactly. This is uniquely determined. Instead of this h, if I want h to be from R2 to, suppose, take R power 100, okay? Such that I want my h of 1 comma 2 to goes to 1 comma to go to 1 comma 1 comma 1 comma 2 comma whatever way you want it to be. Can you just give me some numbers? 3, 4, something, 10, and this is my 100, okay? Something like that. And my 2 comma 1 is, suppose 2 comma 1 comma 2 comma 1 comma, or whatever it is. I mean, we do not even have to imitate this one. Suppose 7, 8, 7, 10, 11, whatever it is. I know h of x comma y is what? This.
The function given above, yes. Minus x by 3, yes.
It is exactly, yes. So I just have to substitute now value of h here. And that's it. My function is now well defined. I don't care what is codomain. As long as I have information about these two here, my function is well defined and unique for chosen value of h of 1 comma 2.
So for any xy we can get a value, no?
Yes. That's
For
what
any
it is,
xy you
right?
can get a value.
For
So once we have the function.
Yes. The moment I fix the value of h of 1 2 and h of 2 1 here, the moment I fix the value, h is defined for everything. That's the power of basis. That's how we the what I said here, which was completely vague at the point. I don't remember. Yeah, this remark which I was trying to say, that the moment I have information of f on the basis, I will have the information of f on any given point. That's what we are doing here. I know the basis of R2. It is, I mean, for this basis of R2, 1 comma 2 and 2 comma 1. The moment I fix the values for these two, my my h is fixed. Yes, sir.
So of course, once you have the knowledge of basis, from the basis we can derive the function.
We don't even want it to be from basis to basis. We just want it from the basis to whatever point in the codomain.
Okay.
This is not even basis of R10, right? This is some point in R10. That's it.
Yeah, that's true. Okay.
Yes. I mean, I can very well define this to be 0, 0, 0. We don't care. Whatever you want, 100, 100, 100, 100, or 10 million, does not matter. That's how.
Can you repeat that sentence? Once you know the values of these two,
Yes, once you know the basis for domain and you have the values of f on the basis, you can have the information about f entirely for any given point.
Because
I mean,
you can have the value of function. I mean, you can
yes,
know
value of function. value of function, because this is what I said na. Sorry, I mean this is what I said so far. Because any point V, if B is a basis V1 to Vn, this any V in V, B is a basis of V, F is from V to W. Any V in V is uniquely determined, uniquely uh, expressed as linear combination of V1 to Vn, of V1 to Vn, right? And this uniqueness will fix everything, because now any V is A1 V1 plus AN Vn. And now if at all this F is linear, if F is linear and exists, and I mean if I have information about F of V1, then I have information about any given V, right? Because this will be what? A1 F of V1 by the property of linearity. And this is unique. This is unique. This will again be unique. And that's how I will have information about F. This is the, what I can say, wrong color. This I can say is the vital, or the, I can say, this is the important part which is giving me this uniqueness. And this is what it is written here, that this H, there exists a unique R linear map. And this is exactly this unique R linear map is. There is no other way this can happen. Okay. And if you want to, yeah, I mean, if, and the moment I have these two fixed, this H of -1, 4, I have information about that as well. H of -1, 4 will be what? I can directly get it from here, from this expression. It is -1. I mean, I'm using this one, okay? Let me box it. This one I'm using. Let me erase this. This is -1, 3 plus, okay, sorry. This is minus of -1 by 3 plus 2 by 3, 4, comma 2 by 3 -1 minus 4 by 3, comma 0, right? And I just have to now do something. This is what? This is 8 plus 1, 9 by 3, comma, this is -2 minus 4. So this is -6 by 3, comma 0. So this is 3, comma -2, comma 0. This is the value of H that is asked. H of -1, 4. And this is the,
which is not equal to 0, 0, 1.
yes, exactly, which is what we had in the previous example here, which is what we wanted here. And see, here also, that's what we got here, -3, 2, 0, because it is unique. Here, I mean, here at this point, we did not even calculate F. Still you saw, I mean, still we can see that this is the value which we got. And here we have the entire expression of F like this, and this is exactly what we got here. So this uniqueness is there because of the basis. Because, yeah, I mean, if I had given that H is something and H of 2, 4 is something, this won't give me uniqueness of H.
Because it's the same thing. Because
yes, exactly.
This
will be
scalar of H1, yeah, 2 of H1.
Exactly. And in that case, I can take one extra element which is linearly independent of this, and I can define whatever I want to that. I mean, I can map that element to any point in R3, and I will get infinitely many such Fs for each choice of that, whatever I choose second element to be. And that will just take away the uniqueness which we have here because of the basis. Is that okay? And that just that just proves the second question as well, right? Because see, f of 1, 2 is 1, 0, 1 here, 2, 1 is this, but f of 1, -1, 4 is -0, 0, 1. This is not happening. This is not the way, because the moment I have these two things, I know how f is. F is exactly h here, okay? This f is also h, and this is also h, right? because here also h of 2 1 comma 2 is 1 0 0 and here this is happening. So this is true. This is correct and this is not. So this one is not a linear map. So f does not exist, g exists. G is precisely h. G is in fact h. Is this okay? This is not. This is the first case which we saw earlier.
Just
Which
so in
was not
second
happening.
question, basically F is not a linear map, but G is a linear map.
Yes, yes, yes.
Okay.
I mean, we can define some way such that f of minus 1 comma 4 is this. Or you can definitely, I mean, just if you just want some map, you can always define it like this, right? I mean, h we know, so it will be f of x comma y will be h of x comma y when x comma y is not equal to minus 1 comma 4, and f of f, I mean, I can define it like this, right? It will be 0 comma 0 comma 1 whenever x comma y is minus 1 comma 4. So this will satisfy all those all these three properties, because of h, f of 1 2 will be whatever that is, f of 2 1 will be 0 1 0, I think, and h of minus 1 comma 4 is this and everything. But this is not linear map, not a linear map. Just defining a function is not a problem, and this is also well defined function. This is just some function. This is some random function. This is just a function. Defining a function is not a problem. We can always define, right? I mean, even for these cases here, you can always define that, I mean, four-step function that f of 1 2 is this, f of 2 1 is this, f of minus 1 4 is this. Otherwise, f is 0. That's it. Done. My function is well defined. But that's not linear map the way we want. I mean, that won't be linear map. That will just be some function. Is that okay?
Yes.
I mean, I hope you got the idea what I'm trying to
Yes,
say.
yes,
Yeah.
yeah.
Yes. So we will do this problem now. I mean, this one, I actually wanted to do this 7.2 because it is complex. We have not taken any example from for complex, but let not do it. We'll do some better question maybe. Sorry for that. Yeah, 7. Yes. This is my third question, I hope. Yeah. So let f from V to V, F and G. From V to V be endomorphisms of a finite dimensional k vector spaces. And k vector spaces V. And if they are saying that if G composed dub F is an automorphism of V, then show that both G and F are also automorphisms. So difference between automorphism and endomorphism is just some map from V to V. When we say it is automorphism, it is bijective map from V to V. Okay, so let me just write. Endomorphism is F from V to V, linear map. That's it. And automorphism, F from V to V, linear map, and bijective. So that is F is isomorphism from V to V. So I'm just writing the definition if you don't know what these terms means. So endomorphism is just any linear map. Automorphism is just bijective linear map. So yes, so what is given that if, and here this is important information, that F is finite dimensional. Okay, so I mean, we'll do this and then we will see one example. I mean, I was not planning that example, but it's nice. So F and G are just endomorphism initially given on finite dimensional vector space, and they are saying that if composition is automorphism, then G and F both are automorphism. So it is like F and G are two functions given, their composition is bijective map, then both of them are bijective map. That's the significance of this. I mean, F is linear is underlined, so we don't have to. Oh, where is it? Oh, yes, just a second. Yeah, so suppose, yes. Yes, so note that since V is finite dimensional, any H from V to V is an endomorphism. If H from V to V is an endomorphism, then the following are equivalent. The following are equivalent. That is first that H is injective, and second that H is surjective. So what this says is that if my f if function is from finite dimensional vector space to finite dimensional vector space, it is a linear function, then saying that f is injective and it is surjective and it is bijective are all same thing. I mean, one will imply the other. I mean, okay, this is because it's finite dimensional vector space. This is not true for any dimension. So because V is finite dimensional vector space, so what we will try to prove here is, so I want to prove that G and F are automorphism. So what I will prove is that F is injective and G is surjective. Okay, so understand that G, so F and G from V to V, endomorphism. I'm just given G composed F is automorphism. To prove that F and G are automorphisms, what we gonna use? If I call this star by star, it is enough to show that F is injective and G is surjective. That's it. Because the moment I have using the star, because star will imply F is bijective and G is bijective. So far it is clear that what we will do, V is finite dimensional. This is important here. Okay, so let us prove then. Given that, so proof of F is injective.
So if we say F is bijective, it means F is injective and F is surjective also, no?
Yes, this is because F is endomorphism on finite dimensional vector space. Because of this, it is on finite dimensional vector space and it is linear.
But you mentioned if it is endomorphism, it means only a map from V to V. It can be
Yes,
injective, it can be surjective. I mean, it may or it may not be.
Yes, it may not be. But here, when I'm saying that it is endomorphism, V is anything, right?
V is anything, right?
Yes. But here, this is extra. I mean, V, if it is finite dimensional vector space, then if H is endomorphism,
Acha,
and if
okay.
H is in, I mean, these three are equivalent, means H is endomorphism such that it is injective, then it implies that it is surjective, and then it is imply that it is bijective. It is not saying that on finite dimensional vector space, every endomorphism is injective, surjective, and bijective. It is saying that if V is such that if V is finite dimensional, H is an endomorphism. H is endomorphism such that if H is injective, then it will be surjective and bijective. If H is endomorphism such that it is surjective, then it will be injective and bijective. And if H is endomorphism or morphism such that H is bijective, then we anyway know that it will be injective and surjective. Is this okay?
So you mean to say if it is given that V is finite dimensional space and H is endomorphism, then
Yes.
H is supposed to be H is by injective, surjective, and bijective, all three.
I mean, it is like saying that three things are equivalent.
Three things are
Means,
equivalent. Okay.
yes, these three are equivalent. The following are equivalent. So if V is finite dimensional and H is a linear map,
Endomorphism.
then saying that H is injective is equivalent to say that H is surjective and bijective. That's what I mean.
Acha, okay. So if anything we
Yes.
prove, then it is automatically understood that it is surjective and bijective also. Okay.
Yes. You can try to prove this. If you do not know the proof of this, try to prove this.
Okay.
Okay, these three are equivalent for finite dimensional vector space. And you can come up with a example. I mean, or you can try to come up with the example, which we can discuss by the end of this proof. Okay. So yeah. So in finite dimensional vector space, and if I have endomorphism, saying that it is injective is equivalent to say that it is surjective and bijective.
Okay.
Yes. So we will just prove that F is injective because V is finite dimensional vector space. So F is injective. So suppose F of V is 0. What we will try to show that for some V in V. Sorry. Then note that G of F of V will be G of 0, right?
Yes.
Sorry. G of 0. This will be 0. So this will imply that G of F of V is 0.
Right.
Yeah. So this, but G composed V is automorphism.
G composed
It is given. G composed V is automorphism. See, given is here. And we have to prove this. So G composed V is automorphism. So automorphism means bijective. That is kernel of G composed F is 0 and image of G composed F is entire V. Right? Bijective, that is isomorphism. That is this. two things are happening, right?
Mm-hmm.
Yes. So kernel is 0. So this implies V belong to kernel of G composed F. That is just 0. So this imply V is 0. So we started with some non-zero, not non-zero, we started with some V such that f of V is 0. Sorry, yeah. And we proved that V is 0. So this imply V is contained. So V is contained in this 0 set. Or we can just, therefore, F is injective, that's it. That's how we do, right? Because, yes. I hope this is okay. Understand that 0 is always contained in kernel of F. And now I'm saying this imply we are choose, suppose V belongs to kernel F. This implies f of V is 0. Or if you want to, suppose V belongs to kernel F. Then f of V is 0. And then, so this implies that kernel of F is 0, right? Because every element in kernel F is 0. So kernel F becomes singleton 0. So therefore F is injective. And using star, therefore by star, F
It is
is
bijective and surjective
bijective
also.
and surjective, therefore it is automorphism. Since F is bijective. Yeah, I mean, you understood what I'm trying to say here. And now we will prove that proof of G is surjective now. And how to do that? That suppose, so how we prove something is what we say surjective, we start with some element from codomain and we find some element. So we start this, if this is V
Codomain to
and W.
domain we have to find out.
Yes. So here, if I choose some element from here, I have to find some element here such that image of this point. So this is why if this is a,
W
then
is
I want to
of
find,
V.
yes. Okay, so that's what I want to find. So suppose, so I'm starting with some element in codomain. So suppose some V in V, then I have to come, so then this, so
I mean,
since,
there exists a V in V such that something.
yes, there exists, so since G composed Fs, see my G is from V to V and G composed F is also from V to V, right? So this V belongs to V is also there in this V. So this, since G composed F is automorphism, there exists some U in where? U in V such that G composed F of V, sorry, there exists some U such that G, right? This is surjectivity of G composed F. Okay, so this implies that G of F of U is V. And this, so what I want, so we can choose. So we set, so we define W to be F of U. This is my element in V, such that then we got that G of W, that is G of F of U, which is V here. So for each V, by, yeah, this, for this V, I could find this W such that F of W, G of W is V. So hence G is surjective as, right?
Ma'am, can you explain one more time?
Yes, sure. So the surjectivity part, right? So what we do is, what we did was, for this G, uh, I started with V here, and I want some W here, such that G of W is V. But what I have is, I have this information. Okay, so this is F, this is G and V. So this is my F and this is my G. Okay, write
Yes, ma'am.
this out. Yeah. So for any element V in this G composed F map, since this map is injective, forget this. Since this is automorphism, there exists some U such that F of this G composed FU is V. If I call this map H, since H is automorphism, there exists some U such that H of U is V, right? But this H, but that is what? G composed F of U. So I'm just simplifying this. This is okay so far. That for G composed F, for this map, I have this U. For this map, I have this U, such that G composed F of U is V. So G of F of U is V. But now this F of U is also in V, right? F is from V to V. And U is in V. So F of U is also in V.
Yes, ma'am.
Yes. So now what I do is, now I have a hold of some element in V such that G of that element is my V. So that's what I define this W to be. This is some element, right? This is some element from V. So if I choose that F to be, this W to be F of U, then my G of W is V.
Okay, ma'am. Yeah.
Yeah.
Yes,
So
ma'am, I
for
got it.
example, yes. For example, if I want to, for example, if I have some, let us say, what? Suppose there is some E here in V. Then for this E, or I don't want to use E. Suppose ABC. Suppose I have this A in V. Okay. Then there will be some B such that G composed F of B is A. But then G of F of B is now my A. So I will again set that C to be F of B such that G of C is A. So what I'm doing is, I'm finding the pre-image of G composed F. And once I have that, that is there because G is given automorphism. G composed F is given automorphism. Then I take F of that thing. This is again some element of V, and that is giving me the pre-image for G. That's what is also happening here. That's what we did here. Is that okay now? And this is
Yes,
happening
ma'am.
because
Yes.
because these are all endomorphisms on V. Everything is from V to V and so on. So we do not have to take care of whether this is in my domain. I mean, the well-definedness of these elements is not concerned at this point, because everything is in V. This image, pre-image, and so on. Is that okay now? And again, using the star, since we are in finite dimensional vector space, the moment I have surjective map, it will be injective and hence bijective. Okay, so therefore G is automorphism as we wanted, using star if we want to do. So this happened because we are in finite dimensional vector space. So can you give me, I mean, do you think this will also happen in infinite dimensional vector space? And if not, then can you give me an example that this star, that H from V to V endomorphism, V finite dimensional, sorry, okay, and this is endomorphism, and the following are equivalent, that first H is injective, H is surjective, this is what we saw, and third H is bijective. Right? These three are equivalent. The moment I say H is injective, other two follow and so on. And we proved that in earlier case that G composed F is automorphism. V finite, F and G from V to V. What we saw that G composed F is automorphism, implies G automorphism, F automorphism. That's what we saw. But so this is my, if I call this star, is star true for infinite dimensional vector spaces, vector space V. Is this possible?
I think sir has said it is not possible.
Yes.
In case of infinite dimensional vector space, it does not hold true.
It does not hold true. So did you come up with example when sir said that it is not possible? Did you try to obtain an example where the composition is automorphism, but F is not automorphism, something like that?
I'm not remembering, but this one I recalled it. He said like this.
Okay. Okay. Try to come up with the example such that decomposed F is automorphism, but F and G are not automorphism, something like that. We here proved that G is surjective and F is so. For example, if we do this, okay, even I am not sure if I want to be injective, right? And G to be surjective. I want G to be surjective. So let us define F from, suppose G composed F is from, suppose V, and V is, or R, infinity is not the correct, Rn, let us take. This you know, right? It is like infinite coordinates. Okay, is infinite dimensional, right? And then I define this F from Rn to Rn such that this x1 to xn is equal to 0, x1 to xn, okay? It goes like this. And is this correct? Let us see, okay? We will switch G and F accordingly, but this works. G, if I take this to be x2, xn. So this is called right shift. and this is called left shift, something like that. This is not correct. I mean, I don't know whether this is correct terminology, but you understood, right? We're just shifting, and this is not the correct way to write this. Sorry. I mean, we are correct, but not entirely. This, and it is just going on like this. And if I take G composed F, yes, then we are correct, right? Then G composed F will be what? G composed F of x1 to xn dot 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 will be, first we are applying F to it. So this will be 0, 1, x1, so on xn here. And then G will be, we are shifting it to, for example, the first one is vanishing and we are just shifting it back. So this G composed F is now essentially my identity map, x1 going to xn and so on. This is identity on Rn. But F and G are not automorphisms. Is this okay? So in infinite dimensional case, that's not true. Just because composition is automorphism does not mean the functions which we are composing are automorphism, which was the case in finite dimensional case. Okay?
Okay.
Yes. So, and these are the examples. This is not injective. This is not injective because kernel is this, right? 1, 0, x1, comma 0, 0, 0. Or I mean, kernel is generated by basis of kernel is this 1, comma 0, so on. Right? And here it is not surjective. It is not surjective. Is this not surjective? Oh, sorry. This is sorry. This is not surjective. This is not surjective, and this is not injective.
Siddhiji, this is
Because
Vinayak here.
Yes,
So
sir.
I need to go for an office call now.
Sure.
It's already okay.
Sure.
I'll drop off. I think this recording
Sure.
I'll see on this
Yeah. Okay. Sure.
website. Last few things of subjective, injective, I didn't understand much, but I've heard it. Okay. Maybe I'll get in touch with you for this separate.
Sure, sir.
Okay.
Yeah. So what I was saying is that yes, this was not injective because kernel of G here is this
yeah,
1,
I mean,
0,
there's
0, 0.
no
Yeah.
there's no image of x1 in the.
Yes. Basis of kernel of G will be this, and this is not surjective because this 1, 1, this thing does not have image, does not have the image. Right? Because whatever the image is, first coordinate is always 0 in the image. Right? So this does not have any pre-image, this in Rn. Okay? So yeah, so this is not, so infinite dimensional case is not good for us for at least these conditions. And one last thing which I would like to, what I can say, which I wanted to do is, yeah, this one. Yes, this is easy. I mean, this one. I think this is question 4 which we are doing. That I will just give an idea and W be a finite dimensional K vector spaces over a field K, then show that dimension K of this. I hope you know what this home KVW means. I will define it once more. Not define, I mean, I will recall it. And in particular, this dimension of K home, this home V to V is actually also endomorphisms, yeah, is dimension K V whole square. This is what, I think this is also statement in the notes, if you remember. This one is there in the notes, and I mean, it is mentioned in the lectures, but it is not proved as far as I remember. Even if it is, let us go through it once more. Yeah, so what we will do is we are asked to yes, prove this thing that dimension is actually not this one. Yes. So to prove this, what we do is this. We just define this map P from V to Vn. So for example, if we have this, sorry for this. Yes. And we try to prove that this map V is in phi is injective. So what we do is understand that suppose this dimension of kv is n, so V has basis v1 to vn, and dimension k of w is m, and basis of w is w1 to wm, suppose, and this home, so home k v comma w is collection of all the f from v to w such that f is k linear map. So when I say k linear map, this the second property of linearity, the coefficient is coming from k, and this endomorphism of k v comma v is again similar, that all those f from v to v such that f is k linear. Okay, so that's just, I'm just recalling the definition. So we have to show that dimension is product of dimension of v and w, dimension of this map, this space, this is vector space, and over k. Okay, this, note that home k vw is k vector space in itself, because we can add two functions such that v going to f of v plus g of v, and we can also do this v going to alpha times f of v. Okay, so this is k vector space. So what we do is we define this map phi from home k v comma w to wn. wn. So this n is v, I mean dimension of v here. So such that this f is now going to f of v1 to f of vn. Okay, so yes, so this v has basis v1 to vn, and as I said that we have hold of the map the moment I have information of it on a basis. So that's what I'm doing. I'm choosing this f. This f is from v to w, and it in each coordinate I'm fixing this f of v1, f of v2, f of vn. Okay, and this dimension of K on Wn is, we can note that it is n into dimension of W. This you can check. So this is n into m. So this you can check. Okay, this you can check. Because this is K dimension. Okay, and yes, and so the moment I have seen. So if we prove that phi is an automorphism, no, this is not automorphism, sorry, is an isomorphism, we get that dimension of this home KVW will be equal to n into m. Because if I have dimension on finite dimension, sorry, if I have isomorphism on finite dimensional vector space, dimension of domain and codomain are equal. Okay, so this phi will be linear map. Phi is linear map. You can check this. You can again check this since we are running out of time. I will just prove the injectivity. Phi is injective part. Phi is injective. And how to do this? Suppose f belongs to this home KVW, right? That's how we are doing it. We start with some element and we show that it is 0. Then if suppose this phi of f will be f of v1, f of vn, this will be some w1 to wn. That is okay. Suppose f is in home and such that phi of f is 0. And when I say this 0, this means this is 0. So that is f of v1, f of vn is 0. So since f of vi is 0,
Excuse me, can I have to go some other class? Can I
yes,
leave?
sure. No,
Yeah.
because the recording will always be there, so you can always
Yeah.
check and come back to me. Yeah, if there
Mhm.
is any. Yeah, sure.
Thank you.
Yeah, sure. So f of vi is 0 for all I between 1 to n, right? Right, and but v1 to vn is what? V1 to vn is basis of v, and we know that the moment I have information about f on its basis, function is well defined. So then f becomes what? F from v to w becomes, for any v, it will be going to, for any v a1 v1 plus an vn, it will go to where? F of this, right? A1 v1 plus an vn. But this is what? This is equal to a1 f of v1, an f of vn. But all this f of vi is 0. So this becomes 0. On the basis, on each element of basis, f is 0. So f becomes 0 function. So therefore, this f in home kvw is a 0 map. And therefore, we started with some f map and turned out that f is a 0 map because each coordinate here, f of v1, v1, v2, vk, whatever it is, at each basis element it is 0. Therefore, it is 0 map. Therefore, kernel of this phi is 0 map. Okay, this 0 here means it is 0 map from v to w. 0 map. Or let me write f from v to w such that f of v is equal to 0 for all v. So this is 0 map. Okay. And now the surjectivity. P is surjective. And so for that, suppose some W1 to Wn, this belongs to my Wn, okay? Then what we do is, then this phi of, then we have to come up with a function in, so we have to find f from v to w such that this phi of f, that is f of v1, f of vn is equal to w1 to wn, right? We have to find such. But what I do is, so what we do is, so we define f from v to w as f of v1 is w1, f of v2 is w2, I mean, and f of vn as wn. Okay, this is what we define. And then for this f, anyway, f of v1 to vn will be w1 to wn. So suppose we want this f, and instead of taking f, we define h such that h of v1 is this, h of v2 is this, and h of vn is this. So h is mapped such that h is from v to w such that h of v1 is w1, h of vn is wn. So this is map we have. So we just set f to be h. And for this h now, then note that p of h will be h of f1, sorry, h of v1, h of vn. And that is exactly my w1 to wn. Because that's how I have defined this h. Okay, so for f, we wanted to find a map from v to w such that this happens, such that it satisfies this equation. And we just define this map h from v to w, because we know that the moment I have information on the basis, I can have the information on the entire domain. So therefore this phi is surjective as well. Therefore phi is automorphism, not automorphism. Phi is an isomorphism, and hence dimension of k whom kvw will be dimension k of wn, but that was dimension k of w into v into dimension k of w. So that's what we proved. And if it was from, and if just using this dimension of whom k v comma v, this is exactly equal to dimension k of endomorphism. This is exactly the endomorphism from v to v. And then this, since both the domain and codomain are same, this will be dimension v into dimension v. And this is just square. This is the spatial case. Okay, and this is what we wanted to show. Okay, so any doubts here? So only thing is to understand this. We define this phi from here to here. Where did we define it? Here. This is something we just want to understand, this and this part. The moment we have this, the rest are just computational or just trying to do things the way we want. Okay. I hope this is okay. Any doubts, please let me know. We are anyway over time. So yeah. If there are any doubts, please. Otherwise, we can end the session. Okay. So since there are no doubts, see you next week. And if there are any doubts, please let me know in the discussion forum. Yeah. Thank you.
Thank you, ma'am.
Yeah, sure.